Hey guys, just a continuation of the previous example. A quick reminder, our sign conventions, okay? So now we're up to the third cut and I want to cut from the right. So just bear into account that the shear force points upwards when cutting from the right. We have a clockwise moment and our axial force end points out to the left, okay? Now just the reason being is the reason they're opposite to cutting from the left is so that they balance each other out, okay? So they have to be in the opposite direction, clearly. So now we're up to the third cut, and let me show you how this one's done when we cut from the right. So the third cut is drawn here. You see, if we drew cut 1 and if we cut it from the left, then we'd have to draw the first cut and the second cut as well, and this gives us much more calculations and it's more tedious and we're more likely to make mistakes. Whereas if we cut from the right, all we have to technically include was the reaction force by the roller and the UDL. So if you look at the original diagram over here, if we cut from the right, then the first cut just includes the roller and the UDL, okay? And the span, sorry, the interval of the cut is from 0 meters, which is over here, since this would be the 0 mark if we're cutting from the right, because it starts from here and ends up 4 meters to the left, which ends just before the UDL ends, okay? So that's our third cut drawn in. It's also a function of x when we cut from the right, same story. The only thing that differs here is the sign convention. Shear force points up, clockwise moment, and an axial force that points out to the left, okay? So now we just do normal equilibrium once again to work out our internal forces. So first of all, we do sum of forces in the x direction equals 0. So since the axial force is the only force horizontally, it equals to 0 kilonewtons. Next we do sum of forces in the y direction has to equal to 0. So we do V, because it points up, so it's a positive V, plus 9.25, because this is the reaction force that points upwards, minus 3 times x. So why is it minus 3 times x? Well, we have a UDL of 3 kilonewtons per meter. It's pointing downwards. We can't add a kilonewton with a kilonewton per meter, so we have to convert the kilonewton per meter into kilonewtons by multiplying by its span, which in this case is x. So it's minus 3 times x is equal to 0. So we find that V is equal to 3x minus 9.25. Since V is a function of x, we need to substitute our extremities, which are 0 and 4. Okay? So when x is equal to 0, V is equal to minus 9.25 kilonewtons. And remember, when x is equal to 0, it's on the right hand corner, since if we're cutting from the right, this is the 0 marker. And when x is equal to 4, we have a shear force of 2.75 kilonewtons, and this is the shear force over here. Okay, 4 meters to the left. Next, now that we found our axial force and our shear force, we need to work out our moment. So how do we work out our moment? We do sum of moments about point B to equal 0, and once again, point B is taken just at the internal actions, okay? So we've got minus m, which is the following moment over here. We have minus m, since it's a clockwise moment, okay? So that's a negative m. Minus 3 times x. Well, now what is this? Minus 3 times x on 2. What is this? This is the clockwise moment caused by the UDL, okay? So the UDL is 3 kilonewtons per meter, okay? So we have to convert it into a point load first, so we multiply by x, okay, because that's its span. Technically, when we convert it into a point load, it's going to be in the center of the UDL. So if it's at the center of the UDL, the lever arm then is going to be x over 2 from point B. So as you can see, it's minus 3 times x on 2, okay? Then we have plus 9.25 times x, and this is from the roller over here. It's causing an anti-clockwise moment about point B, and it has a lever arm of x, okay? So rearranging all this, we find that our moment equals to minus 3 on 2 x squared plus 9.25 times x, okay? Now as you can see, it's also a function of x, so we need to substitute our extremities, which are 0 and 4. So when x is equal to 0, m is equal to 0 kilonewton meters, and when x is equal to 4, m is equal to 13 kilonewton meters. Okay? Now, since the moment is a polynomial of degree 2, there's definitely, and this is from calculus, there's going to be a maximum bending moment or a minimum bending moment. So how do we work this out? Well, we have to differentiate the moment once and set it to equal to 0. Okay? So if this is our moment equation over here, we differentiate dm dx is equal to 0. We find that dm dx is equal to minus 3x plus 9.25. Just simple differentiation of the following equation. So we have minus 3x plus 9.25. We set this equal to 0 and we solve for x. We find that there's a maximum or a minimum bending moment, 3.08 meters to the right. Okay? So we go back and substitute x equals 3.08 meters. We substitute this into the moment equation. Okay? And we find that we have a maximum bending moment of 14.3 kilonewton meters. So make sure you understand that when the moment has a degree polynomial 2, okay, or excuse me, a polynomial of degree 2, there's going to be a maximum bending moment or a minimum bending moment. The way we work this out is we differentiate the moment once and we set it to equal 0. We solve for x. We substitute the x value into the moment equation, which is in this case here, and we found that the bending moment was 14.3 kilonewton meters. Okay? Now that this is all solved, we can simply draw in our bending moment diagram, shear force diagram, and axial force diagram. So first of all, we draw our initial structure in, which was this. We draw the axial force diagram under it. Now we saw that N was equal to 0 in every cut, so the axial force diagram was just 0 kilonewtons. Next we have the shear force diagram. We saw that in the first cut we had a shear force of 3.75 kilonewtons, so it's just a constant of 3.75. In the second cut, which is from here to here, we saw that we had a shear force of 2.75 kilonewtons, once again a constant. In the third cut, we saw that the shear was a function of x, and therefore it's a linear line, and the shear values in the third cut were 2.75 kilonewtons down to minus 9.25 kilonewtons. Okay, because in the third cut we cut from the right, we said when x is equal to 0, v was minus 9.25 kilonewtons, and this occurs over here, and when x is equal to 4, v is equal to 2.75 kilonewtons, which is over here. Now if we're cutting from the right, just remember that this is the 0 marker and this is the 4 meter marker, but when we cut from the left, this is the 0 marker, obviously, because we start here. Okay, so next we draw our bending moment diagram in, and guys, please remember your units, very important. Okay, in the first cut we saw that the moment was a function of x, so it's linear, and it went from 0 to 7.5 kilonewton meters. In the second cut, it was also a function of x, okay, and it goes from 7.5 kilonewton meters to 13 kilonewton meters. In this third cut, it was a polynomial degree 2, so it's going to be a parabola, and there's going to be a maximum or minimum bending moment. So as you can see, it started at 13. At x is equal to 3.08 meters from the right, which is approximately here, there was a maximum of 14.3 kilonewton meters. So it goes up to a peak of 14.3, the parabola, and finally dropped down to 0 meters at this mark here, to 0 kilonewton meters at this mark here. And that's our bending moment diagram. So guys, please make sure if you can take advantage and save yourself some time and less tedious calculations by knowing your sign conventions and understanding your sign conventions. This leads to effective results and you can save a lot of time. Okay? But if you're not very confident with it, then stick to one side and cut consistently from that side. So I hope this video has helped you understand how you can cut from both ends. Thank you for listening.